We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
In 1977, the Space Shuttle Enterprise performed its first low-speed flight trials. These unique flights made history. They were the first step in our ability to travel in space and return on a regular basis. The location of these flights was unique, too. NASA's Hugh L. Dryden Flight Research Center. Dryden sits on the edge of Rogers Dry Lake, a 65-square-mile expanse of tough, sun-baked clay. It has a rich tradition of accomplishment. It was the location of the world's first supersonic flight and first hypersonic flights, many of which also went into space. NASA's predecessor, the National Advisory Committee for Aeronautics, established Dryden in 1947 to test fly the X-1, the first airplane to go faster than sound. The center's personnel first proved that manned supersonic flight could really be done. They did it with the X-series aircraft, such as the delta-winged XF-92A Dart and the D-558 Phase 2 Skyrocket, first plane to fly twice the speed of sound. The X-3 found and probed dramatic roll stability problems in supersonic jets. And the bat-like X-4 researched pitching instability, which jeopardizes tailless airplanes. The X-5 was a variable sweep plane. It proved that such aircraft can fly. With wings extended, it excelled at low speeds. With wings swept, it performed well at high speeds. At the same time, the Air Force was flying the X-2, the first plane to reach Mach 3 and nudge the thermal barrier. NACA engineers designed their own advanced research plane based on the X-1. This was the X-1E. It could fly twice the speed of sound and had an experimental wing configuration. The X-1E now is mounted in front of Dryden Flight Research Center, a monument to those early years that gave the world supersonic flight. From 1958 to 1968, Dryden test flew the X-15. It was the first airplane to explore the region of aeroheating and fly above the atmosphere. It reached speeds of 4,500 miles per hour and got to altitudes of 67 miles. The X-15 pioneered re-entry from space to an aerodynamically controlled landing. Dryden's research extends to all kinds of airborne vehicles. To support the moon landing, our engineers designed the Lunar Landing Research Vehicle, which simulated a descending lunar module. Apollo astronauts practiced on these flying simulators before they attempted the real lunar landings. In the late 1960s, Dryden flew a test program exploring the characteristics of large supersonic cruise airplanes. The XB-70 contributed to the design of supersonic transports. One of Dryden's most exciting programs was the YF-12 Blackbird. Our pilots and engineers tested two of these aircraft in the late 1970s. The Blackbirds were capable of sustained flight at Mach 3 speeds and 80,000-foot altitudes. Our tests with the YF-12 studied handling qualities, high-temperature structure effects, and performance of the exotic turbo ramjet engines. NASA's Parasev explored the possibility of using flexible wings, which would allow returning spacecraft to land at conventional airfields. Results left a lot to be desired. and the idea was grounded. In the early 60s, Dryden began testing a group of aircraft called lifting bodies. The plywood M2F1 was the first, towed aloft by an airplane, then released to land as a glider. Half spacecraft and half aircraft, lifting bodies were designed without wings, so they might re-enter the Earth's atmosphere with a minimum of structural and heating problems. Success with M2F1 tests led Dryden engineers to develop the M2F2. In contrast with its light, unpowered predecessor, this craft was a rocket-propelled heavyweight. The M2F2 demonstrated that this shape can fly at the high speeds representative of vehicles entering from space. The HL-10 represented another lifting body design approach. Like the M2F2, the HL-10 was a heavyweight vehicle equipped with rockets. It first flew in late 1966 and attained the maximum speed and altitude records for lifting bodies. The HL-10 reached speeds approaching Mach 2 and altitudes greater than 90,000 feet. The X-24B lifting body was a joint NASA and Air Force research project. This craft was launched from a B-52, then boosted to high altitudes by rockets. Body shape alone gave these aircraft the aerodynamic lift needed to fly in the atmosphere. The pilot stabilized and controlled the craft by using its fins and control surfaces. Information from all the lifting bodies contributed substantially to developing the space shuttle. The X-24B proved that a shuttle could return from orbit to unpowered landings on a conventional runway. The payoff from lifting body research started to show in 1977, when the shuttle Enterprise performed approach and landing tests at Dryden. After it was dropped from NASA's 747, the Enterprise glided to unpowered landings, one of them on the concrete runway. These successful landings were the final step in preparing for the return of real shuttles from spaceflight. Dryden researchers are using an F-111 to study ways of developing more efficient wing shapes. In the natural laminar flow experiment, they modified the plane's outer wing panels. This new wing shape eliminated turbulent airflow over much of the wing surface. Another project geared to improve aerodynamic efficiency was winglets. Engineers modified this KC-135 transport by mounting vertical extensions on its wingtips. These winglets act to increase lift and lower drag. Flight tests showed that winglets improve the airplane's fuel economy by 6%. One of the most unusual and highly experimental aircraft ever tested at Dryden was the Gossamer Albatross. The Albatross was human-powered and pedaled like a bicycle. Dryden researchers added a small motor so they could measure power usage. Construction of the Albatross was made possible only by the latest state-of-the-art lightweight structural materials. The plane weighed just 55 pounds, but had a wingspan of 96 feet. The man who designed the Albatross also built the world's first flight-worthy sun-powered plane, the Gossamer Penguin. The Penguin was a 3/4 scale version of the Albatross, but modified for solar flight by a panel of cells. Electricity from the cells ran a motor, and the motor turned a rear-mounted propeller. One of the most dramatic problems studied here was wake vortex. Wake vortex is a turbulent air condition that forms at an airplane's wingtip. It's caused by pressure differences above and below the wing. The resulting vortex jeopardizes other aircraft behind it. The wake vortex from a large transport can throw a smaller plane out of control and even cause it to crash. wake vortex became a big threat with the introduction and growing use of jumbo jets. An effort to reduce its hazards became a matter of national priority, and NASA teamed with the Federal Aviation Administration to learn how the vortex works and alter its effects. By comparing upsets of probe aircraft flying in the wake, they proved that using selected combinations of wing flap, spoiler, and landing gear positions, they could effectively reduce the strength of the vortex. Dryden's F-8 flight tested a vital system of the space shuttle. This is digital fly-by-wire, a combination of 3 digital computers with a fail-safe backup computer installed in the plane to control all of its operating functions. Lightweight wires and electronics replace mechanical linkage and translate the pilot's signals through the computers to the plane's control surfaces. Digital fly-by-wire frees the pilot from details and allows him more time to make the command decisions required by a mission. NASA is supporting the military by testing advanced fighters. The F-15 is an Air Force high-performance plane. Dryden has 2 of these aircraft and is using them in a wide variety of experiments. We are conducting tests with the F-15 to better its engine performance. Our research could lead to new technology in afterburning turbofan devices, in combating stall spin at high angles of attack, and in computerized electronic engine control. The F-14 is a Navy high-performance fighter. Researchers at Dryden are experimenting with its control system to improve its flying ability during combat-type maneuvering. While performing certain extreme maneuvers, pilots have had problems with spin and loss of control. Control modifications done here have made the F-14 easier to fly. For functional versatility, one of the most promising ideas tested here is the tilt rotor. This aircraft is a cross between a fixed-wing airplane and a helicopter, and it has the advantages of both. As a helicopter, it can hover and take off vertically. As an airplane, it can reach speeds much higher than any helicopter. The tilt rotor is powered by 2 engines located in its wingtip nacelles. To make the transition from helicopter to airplane, the pilot tilts the nacelles from upright to forward. As an airplane, the tilt rotor has flown at speeds of almost 350 miles per hour. Research pilots find it easy to fly and very stable in the hover position. Safety is a big feature of this aircraft. It is built with many redundant fail-safe systems, so no failure of a single subsystem can pose a critical threat. The tilt rotor's flexibility and safety features make it highly attractive for both industry and military use. Its ability to hover or put down where no runway exists makes it a likely candidate for transportation to remote locations or possible air-sea rescue duty. The C-140 Jetstar has served as test bed for many Dryden experiments. This versatile plane currently is test flying an advanced propeller model, which should lead to considerable fuel savings in future aircraft. This prop fan is 1/7 the size of the full-scale propeller. Researchers are using it to measure noise levels. The Jetstar performs most of the tests at 8/10 the speed of sound. Designers of future high-speed turboprop airplanes will use the information to design quieter propellers to minimize cabin noise. The Jetstar also test flies the microwave scanning beam landing system used by the space shuttle when it returns from orbit. One of the most exotic aircraft ever flown at Dryden is the AD-1. This airplane has a single wing attached to the fuselage through a pivot assembly, so it can swivel to oblique angles. The idea here again is to save fuel. During takeoff and landing, the wing can be positioned at right angles to the body for maximum lift. But as the aircraft picks up speed, the wing can be pivoted to cut down drag and therefore fuel usage. Dryden pilots have successfully flown the AD-1 with the wing pivoted to 60 degrees, its maximum angle. Researchers are studying results of the tests to develop future aircraft using the oblique wing concept. The built-in dangers of flight testing showed up during this evaluation of the PA-30 twin Comanche. Dryden engineers were flying it to study operating problems of general aviation aircraft. The plane had a serious flutter problem, which appeared unexpectedly. Fortunately, the flutter did not cause a catastrophic structural failure, and the NASA research pilot made a safe landing. Another flutter problem that occurred here posed no threat to the life of the pilot. This was a test with the DAST, short for Drones for Aerodynamic and Structural Testing. DAST is a remotely piloted vehicle. The pilot controls the plane from a ground cockpit through uplink signals. This is a cost-saving method of testing highly experimental aircraft. This one proved unstable. Dryden researchers developed a remote piloting technique for aircraft too hazardous to be tested by an onboard pilot. An outstanding example of such an aircraft is HIMAT. Air-launched from the B-52, the HIMAT is powered in flight by a turbojet engine with afterburner. HIMAT stands for Highly Maneuverable Aircraft Technology. From the ground-based remote cockpit, HIMAT's pilot sends commands to computers aboard the aircraft, causing it to pitch. Another command initiates a roll. Highly sophisticated computerized systems on board the craft and in the remote piloting chamber give the pilot as much control as he would have if he were actually on board an airplane. The HIMAT is designed to pull 8 Gs, that is 8 times the force of gravity, in sustained turning flight, while traveling 9/10 the speed of sound. This is almost twice the turning capacity at transonic speeds of any fighter now in use. To achieve such futuristic capabilities, HIMAT designers combined state-of-the-art technologies, including digital fly-by-wire, advanced fighter aerodynamic configurations, winglets, aerodynamic tailoring, and super lightweight carbon graphite structural materials. Once test maneuvers are finished, the pilot uses a television system installed on board the HIMAT to land his plane. When HIMAT lands, it's traveling about 240 miles per hour. One of our F-15s has served as test bed for a number of aerospace innovations. Perhaps its most important contribution to new technologies was flight testing heat shield tiles for the space shuttle. For research purposes, tiles were fixed to the wing and nose. Thanks to these tests, we learned a great deal about thermal tiles and how to attach them for flight in the atmosphere. When the Enterprise performed its approach and landing tests at Dryden, it discovered a problem of great urgency in shuttle landings and in maneuvering of all fly-by-wire airplanes. The problem is known as pilot-induced oscillation, or PIO. It happens when the aircraft's controls don't respond to the pilot's commands as fast as he expects. The pilot automatically assumes the controls didn't get the message, so he repeats his command. Meanwhile, the computer is executing the first command, so the pilot reacts by trying to compensate for the extra command. The result is PIO. To solve the PIO problem, Dryden researchers turned again to the F-8 digital fly-by-wire. For these tests, engineers programmed the F-8's computers to make the plane particularly susceptible to PIOs. The pilot flew the plane in the oscillation vulnerable mode and tried a series of PIO suppression filters to find which one worked best. These F8 tests produced a good suppression filter for the shuttle, and Dryden researchers are continuing tests with the F8 to produce workable suppression filters for any fly-by-wire aircraft that may have a similar problem. Flight simulators have been used at Dryden since the X series. They precede in-flight research and enable experimenters to evaluate how a plane will perform under flight conditions. They allow researchers to investigate hundreds of variations before committing an airplane to flight. In the case of the space shuttle, the flight simulator is more important than ever before. This is because the shuttle is such a complex machine, flies in such a wide range of atmospheric conditions, and at Mach 25, travels much faster than any plane has done before. The maiden voyage of the space shuttle began on April 12, 1981. A combined blast of solid rocket boosters and main shuttle engines sent the Columbia, the world's first reusable spaceship, hurtling from its launch pad at Kennedy Space Center toward its first orbital mission. The spectacle attracted cheering onlookers and photographers from around the world. Most of the shuttle's fiery appearance came from its two solid rocket boosters. The boosters burned out about 2 minutes into the flight and were jettisoned. They fell back into the ocean and were recovered for use on later missions. The shuttle continued toward orbit, powered by its main engines supplied with propellant from the huge external tank. Astronaut Robert Crippen served as pilot of the Columbia's two-man crew under Commander John Young. They steered the Columbia into proper orbit by using the Orbital Maneuvering System engines. During the two-day mission, Young and Crippen had a full workload of scheduled duties to perform. After orbit was achieved, the astronauts changed from pressure suits to casual work clothes. This, plus the ability to float freely in the non-gravity of space, made getting around the working compartments fairly easy. Before returning to Earth, however, the men were required to return to their pressure suits, a process which takes about 2 hours. Taking pictures of the Earth was one of the astronauts' duties. Thousands of spectators gathered beside Rogers Dry Lake to witness the first landing of the Columbia. Many had spent the night to ensure a good viewing spot. After circling the Earth 36 times, Columbia was given a go to re-enter the atmosphere. 30 minutes later, Columbia was over Rogers Dry Lake, making its approach to runway 23, precisely on target. And the long-waiting viewers were not disappointed. Thanks to its thermal tiles, it easily survived temperatures of 2,300 degrees Fahrenheit. The first spacecraft ever to land as an airplane was guided to a perfect touchdown by her astronaut crew. It marked the beginning of a new era in which man can travel to space and back using the same vehicle. Commander John Young was first to emerge after landing. Jubilant over the mission's success, he called the Columbia a fantastic flying machine. Within minutes after landing, the machine was being serviced by a convoy support team. Bob Crippen finished his post-flight duties and debarked, following Young, to an enthusiastic greeting by members of the convoy. The astronaut van, part of the convoy, took both men to their post-flight medical examination. The mission culminated at Dryden in a lakebed ceremony. It was a joyful welcome for the astronaut research pilots after the greatest history-making test flight of all time. Dryden will continue to be a prime mover in the evolution of flight. As aerodynamic innovations are made and experimental frontiers crossed, our people will always be at the leading edge of research.
Sunday, April 12, 1981, Kennedy Space Center, Florida. The Space Shuttle, 14 stories high, 2,000 tons, poised on the pad for its maiden flight. This is Columbia, the spaceship that will orbit the Earth. Its external tank, it holds over 500,000 gallons of fuel for Columbia's 3 main engines. And the solid rocket boosters, the largest ever used on any launch vehicle and the first to be employed in a U.S. manned flight. At liftoff, the solid rocket boosters, together with the 3 main engines, will unleash more than 6.5 million pounds of thrust needed to launch the world's first reusable spacecraft. Never before has a winged vehicle been launched like a rocket, orbited the Earth, returned through frictional heating in excess of 2,500 degrees, and landed, still aerodynamically sound, to be launched again and again. If it succeeds, the space shuttle will truly be a remarkable flying machine. There are many other goals to be reached during the 54.5-hour mission that lies ahead. 144 test objectives are planned for the flight. These objectives could not be achieved without an astronaut crew. The commander, John Young. The pilot, Robert Crippen. Young has already been in space 4 times for a total of 533 hours. He is the most experienced astronaut flying today. Although Crippen has over 4,000 hours of jet aircraft flying time, this will be his first time in space. The astronauts make their way across the access arm toward the shuttle in the pre-dawn hours before launch. An American spaceship has never carried a human crew on its maiden voyage. At the Launch Control Center, 3 miles from the pad, final steps are being completed in the countdown. Final preparations are also being made in the Mission Control Center in Houston, where control of the flight will switch once the shuttle clears the tower. There has not been a manned launch from Kennedy Space Center since the Apollo-Soyuz test project in July of 1975. With this launch, Young and Crippen, launch controllers at the Cape, and flight controllers in Houston will experience the most dynamic, fast-paced series of launch events ever undertaken in the space program, all in less than 9 minutes. The most challenging ascent profile ever to be flown by a space vehicle. Photographers, film and television crews, plus newspaper and magazine writers from around the world, nearly 2,700 of them are here to cover the launch. In addition, approximately 600,000 spectators line the coastal area near the Kennedy Space Center. Arriving by every mode of transportation, they have come from every state in the Union and many foreign countries. The promise of a rebirth in America's manned space program and the dawn of a new era in space transportation awaits.
14, 13, T-minus 10, 9, 8, 7, 6, 5, 4. We've gone for main engine start.
Roger, roll.
The roll will put the shuttle on its precise heading toward an imaginary target in space.
Roll program complete.
Roger, roll complete.
Get a status, Fido.
Go.
Booster.
Go.
GNC.
Go.
Eagle.
Go.
Go at 40, Capcom.
Columbia, Houston, you're go at 40.
The shuttle is now 40 seconds into flight.
Roger, Columbia, on the nice ride. You're lofting a little bit. You'll probably be slightly high at staging.
Negative seats.
Columbia, you're negative seats.
Should anything go wrong, the shuttle is now too high for the astronauts to use their ejection seats.
Roger, you're go for SRB SEP.
We see SRB SEP flight.
Roger, on a SEP.
103 converge flight.
Vet. Capcom, let's tell them all the calls are going to be a tad early because of the hot first stage.
Columbia, you're looking a little hot. All your calls will be a little early.
Okay. And that looks good here. Stand by, press to MECO.
Columbia, stand by. Press to MECO.
Mark it.
Marked. Press for MECO.
Roger, press for MECO.
The shuttle can now continue toward MECO, main engine cutoff.
They like your VAP, Eagle. ECOM.
Let's go, flight.
Capcom, VAPs go.
Stand by, negative return.
Columbia, stand by for negative return.
Mark it.
Marked. Negative return. And your VAP is good.
Outstanding. Sure is. We can confirm it. What a view. And single engine rotor flight.
And Columbia, your single engine rota.
Columbia can land safely at the Naval Air Station in Rota, Spain, even if 2 of the 3 main engines should fail. Right now, the engines are generating over 42 million horsepower.
MECO 25, 6,
MECO.
0, up at 220.
Roger, MECO.
And we got MECO confirmed.
MECO
Roger,
confirmed,
Columbia,
and it's
MECO.
right on the money, nominal.
Main engine cutoff. Columbia is now in space, traveling over 18,000 miles per hour.
Okay, we got set.
Roger, we confirm the SEP, Columbia.
The external tank has just been jettisoned and is now falling away from the shuttle back toward Earth. The tank will break up as planned over the Indian Ocean when it comes into contact with the atmosphere. Shortly, by firing the OMS, Orbital Maneuvering System engines, Columbia will achieve orbit. Then one of the most important tests of the mission will be attempted, opening the payload bay doors. The doors must be opened before the end of the 6th orbit to expose the space radiator cooling system. If the radiators cannot be exposed, heat collected from the onboard electronics cannot be released, and the astronauts will have to return home. The Ohms burns are successful. Columbia is now in orbit, circling the Earth at an altitude of approximately 150 miles. The payload bay doors will now be opened.
Okay, the port door's coming open now.
Roger, copy.
Well, you are missing one fantastic sight. Boy, that is really beautiful out there.
We appreciate those updates.
Both doors have been opened. The radiators can be deployed to begin dissipating the heat.
The doors are all opened up and hunky-dory. Glad to deploy right on time.
And the radiators look good.
Okay, we want to show you our home spots here. We do have a few tiles missing off of both of them. Off of the starboard pod, 3 tile and some smaller pieces, and off the port pod, looks like I see one full square, and looks like a few little triangular shapes that are missing, and we're trying to put that on TV right now.
Roger, Crip, we can see that good.
From what we can see of both wings, tops and leading edges, though, all those are fully intact.
Within minutes, an assessment is completed on the impact these missing tiles could have on the remainder of the mission. At a news conference later in the day, Flight Director Neil Hutchison answers questions from reporters.
Well, you asked me if I knew where there were any other tiles that might be loose. The answer is no. And quite frankly, we're not worried about any other tiles being loose.
At this writing, is there anything at all that would lead you to say you might not go for a full duration mission?
Nothing.
Columbia, Houston, you guys did so good, we're going to let you stay up there for a couple of days. Your gopher on orbit.
Spacecraft let's go for on orbit. This thing is just performing just outstanding.
Roger, we agree with that. And Columbia, Houston, just for your information, you dropped those SRBs right on target, and they were floating just the way they ought to be, and the boats were getting ready to fish them and bring them back.
Okay. The ride that they gave us was pretty neat.
The solid rocket boosters, which separated from the Columbia as planned 2 minutes 11 seconds into the flight, landed on target in the Atlantic Ocean, 151 miles downrange from the launch site. After being towed back to Kennedy Space Center, both boosters will be refurbished and used again in a future shuttle flight. The 3rd and 4th Ohms burns are also successful, raising Columbia's orbit to an altitude of approximately 172 miles. For the first television transmission from inside the spacecraft, the crew will give a status report on the mission.
The flight so far has gone as smooth as it could possibly go. We've done every test that we're supposed to do, and we're up on the timeline, and the vehicle has just been performing beautifully, much better than anyone ever expected to do on a first flight, and no systems are out of shape. And it's delightful up here in zero gravity, might add. Of course, we owe this to a lot of people. So we certainly want to thank everyone who has helped get this thing airborne, and can take great pride in doing so well right now. Okay, we're switching over to the aft camera here. Yeah, I'd like to echo John's words as I usually do. I guess being the so-called rookie on this flight, I had a thrill from the moment of liftoff all the way up to what we're doing now. It's really been super. The spacecraft has worked as advertised all the way along. I think we've got something that's really going to mean something to the country and the world. This vehicle is performing like a champ, like all of us that have worked so long on it knew that you would.
Okay, sir, we appreciate those comments.
I guess that does it.
That was good timing. I think you must have practiced. We're just about to lose your gold song.
Just accident.
Just accident, says Robert Crippen. None of the other events of the day have been accidental. Every test, liftoff, SRB separation and recovery, ET separation and impact, 4 ohms burns, payload bay door latch opening and closing tests, radiator latch deploy and stowing tests have all been successful.
I guess we owe you guys one super attaboy for today. This is fantastic. You worked through a pretty long, hard day, and you're essentially right on schedule, which is going to be close to being a first sort of spaceflight biz, I think, for first day activities. It's sure been fun working with you today, and we look forward to seeing you in the morning. I hope you get a good night's rest.
Okay, you guys did super work today. See you mañana.
Roger, thank you. See you tomorrow, guys.
Well, many hours went into this thing. A job well done by the shuttle space team. We can't say she's sleek and lean, but I'll tell you right now, she's a mean machine. The Columbia, not the kind you smoke. This here's a bird.
Morning, Columbia. Welcome to day 2.
All right. Appreciate that super wake-up music this morning. Well, we sure enjoyed it. This one a good breakfast.
Today, the astronauts will test onboard systems and also review procedures for tomorrow's landing. A test of the flight control system is conducted by John Young. The flight control system operates Columbia's aero surfaces, the elevons, body flaps, rudder, and speed brake. These surfaces are useless in the vacuum of space, but will be essential tomorrow when the shuttle lands. This will require precision maneuverability, which the aero surfaces provide. Payload bay door cycling tests help ensure that latching and closing procedures can also be done before entry tomorrow. As with every mission, many pictures of the Earth are taken by the astronauts. Over 500 on this first shuttle flight. Active volcanoes, cloud formations, alluvial fans, giant whirlpools over 15 miles in diameter, sand dunes 1,500 feet high, running unbroken for hundreds of miles. The high Himalayas, where mountain peaks reach 24,000 feet. And one of the most remarkable space photographs ever taken of the Earth, an area in Iran exposed to wind erosion, which has resulted in these breathtaking silt and sandstone formations that look more like a painting than a desert. After lunch on the second day, the astronauts receive a phone call from the Vice President of the United States, George Bush.
How's it going up there? Everything rocking along all right?
Spaceship is just performing beautifully.
Well, it's great, and everybody views it, I'm sure, just as the forerunner of great things to come. I think your trip is just going to ignite the excitement and the forward thinking from this country, so I really just wanted to call up and wish you the very best.
We certainly appreciate it, Mr. Vice President.
The crew also don and check out the ejection suits they will wear during entry. Young, Crippen, and Columbia pass every test. They are ready for the final phase of the mission, entry and landing. April 14th, 1981. NASA's Dryden Flight Research Center on the edge of Rogers Dry Lake Bed in California. A A recovery convoy of 24 vehicles and more than 100 personnel are assembling here to power down Columbia after landing. Enormous crowds are also beginning to arrive. A string of traffic 6 miles long waits to enter the base. Thousands more are already here. Close to 500,000 people will eventually be on hand to see the landing. On board, the astronauts suit up for entry. The ascent and orbital phases of the mission have gone extremely well. Now the final phase must be completed. Before that begins,
Columbia, you have a go for payload bay door closing.
the doors, which have been opened a total of 47 hours during the flight, must now be closed. Then, using the RCS thrusters, Columbia will maneuver into deorbit burn attitude, head down and backwards, fire the OMS engines one last time, and descend into the Earth's atmosphere.
Nice and easy does it, John. We're all riding with you.
Columbia is out of contact during the OMS burn. Mission Control will not know if this burn was successful until they are in communication with the spacecraft over Australia. It is now over the Indian Ocean on the other side of the world, but from that distance the burn must be precise so that later Columbia will hit the lake bed target in California.
Columbia, this is Houston through Yargady. We're standing by.
Burn was on time at nominal residual 110.
Columbia is now committed to entry. With an RCS post-burn maneuver and several firings, it is oriented to a heads-up, nose-first attitude headed toward entry interface. This is where the atmosphere begins, at approximately 400,000 feet.
John, we copied,
From that moment until the shuttle reaches 165,000 feet, it will be in communication blackout, out of touch with mission control for almost 20 minutes. The landing site is almost 4,400 miles from entry interface. Chase planes are preparing to take off. One will call out altitudes and check Columbia for any damage just prior to landing. When the shuttle touches down here, it will be traveling at 216 miles per hour. Right now, it's going more than 17,000 miles per hour. Before it lands, it must slow down, lose energy, and it must survive the intense heat caused by traveling through the atmosphere at such a high rate of speed. Several S-turns or roll reversals are used to slow down and maneuver Columbia through the atmosphere. This one is done at 256,000 feet when it is traveling at more than 26 times the speed of sound. This one is done at 208,000 feet. During these two roll reversals, entry heating is most severe, with temperatures reaching 2,500 degrees some places on the vehicle. The aluminum skin will melt at 320 degrees. The silicate tiles must insulate the vehicle from the tremendous heat. Since there is no test facility on Earth to simulate the aerodynamic and structural environment Columbia is in right now, only calculations could be used to predict what would happen during this phase of the flight. The predictions and calculations had to be right.
Hello there, Houston. Columbia's here.
Hello, Columbia. Houston's here. How do you read?
Plan clear, and we're doing Mach 10.3 at 180 AS.
And we couldn't agree more, John. Your state vector's good. We've got good data in-house.
Okay.
The entry trajectory, velocity, and position look good. Columbia is heading for home, now only 470 miles away.
Nothing more left RCS, but okay.
Right, we're showing you roll. And John, we're showing you rolling right. Looking good.
Right, normal roll.
We're showing him crossing the coastline flag.
Columbia, we show you crossing the coast now.
The shuttle is first sighted at about 100,000 feet with a long-range camera from Anderson Peak, California.
What a way to come to California.
In flight pattern, I still look perfect right on the nominal.
Roger that. Out of 112K, 4.8 Mach.
Push me up this rope.
We see Delaz 21 degrees.
A role reversal is done over Bakersfield, California.
Oh, that's beautiful.
Chase has a tally.
Roger, Chase.
And we're seeing 1.3 Gs coming around the hat.
Roger that.
The astronauts are making the final turn to line up with the runway.
Columbia, you're really looking good. Right on the money. Right on the money. And turning on to final, your winds on the surface are calm.
I got a win.
You're right on the glide slope, Columbia.
Yeah, we're gone.
Looks real good underneath. Everything looks real good.
Chase reports no tile or other damages evident underneath the shuttle. Columbia's altitude is now just over 5,000 feet.
Pretty clear.
Without power, Columbia must land. It cannot make another attempt.
They're coming. You're down. Feet. 40, 30, 20, 10, 5, 4, 3, 2, 1, touchdown. Those gears, come. 5, 4, 3, touchdown. Look it off, skipper.
Columbia's on the roll.
Welcome home, Columbia. Beautiful, beautiful.
You'll have to take it up to hangar, Joe.
We're going to dust it off first.
This is the world's greatest all-electric flying machine, I'll tell you that. It was super.
Okay, convoy's on its way.
Convoy on. We'll stop on the Columbia. We'll stop.
The maiden voyage of Columbia has been a success. The astronauts and the vehicle have met or exceeded all 144 flight test objectives. The integrity of all the systems, propulsion, avionics, structural, flight control, power, and thermal have been affirmed. John Young's comments after returning home.
I can't tell you what a tribute that is to the American working man and the American working woman, too. You can't imagine the variety of people who worked on this vehicle, from all walks of life, all capabilities and limitations. It's all due to their individual efforts. They proved that they can do the job. They proved it for the world to see. And I'm mighty proud to be associated with folks like that.
What a tribute indeed. The Columbia represents an achievement in aerospace technology and development never before realized in the history of manned spaceflight. It is our basic building block for the future.
It's what we've been trying to do for the last 10 years. We've got a vehicle with a payload performance that will allow us to do that, much cheaper than we've been able to do it before. It will immeasurably improve the defensive capability of the country. It will help develop space science and technology. When we get operational, the space shuttle will be able to do in 5 to 10 years what it would have taken us 20 to 30 years to do otherwise. We couldn't do it if we didn't have the space shuttle and that payload capability. And the sooner we do those things, the better off the country's going to be.
A revolutionary new era in space transportation has just begun. Routine access to space. Welcome to the future.